Could all join me in turning off your video and muting yourself so people with a low bandwidth can also enjoy the full talk. And then I have the pleasure to introduce you to Nushki, one of our very knowledgeable data scientists. And she has a PhD in topology, and she has paid large attention to graphs. And today she's going to share some of her extensive knowledge with us. Nushki?
Thanks so much for very kind introduction, Marcus. I'm going to try to share my screen, and let's see how we go. Can you see my slides?
Yes.
Awesome. So I also pasted the slide link. You can probably see where I've pasted it. So you can get the slides if you want. So since I joined Eliiza last year, been working on a few projects, and I was really surprised, but in retrospect, I really shouldn't have been surprised to find that graph theory was coming in handy in almost everything I did. And of course, I'm probably biased because I've been working with graphs quite a bit, and I'm probably seeing them in places quite a bit. But it was a really pleasant part of being a data scientist to realize that a lot of my maths work in graph theory was coming in handy and was making some of our solutions more interesting, was making them work better, and just like helping us frame some of the problems in sort of visually and intuitively accessible ways. So just to give you a little bit of background on where my graph theory interest comes from and how that's related to how that has sort of surfaced in my data science work. When I started working on my PhD a decade ago, one of the first things my advisor asked me to work on was a puzzle, basically, to figure out if some of the finite graphs had a certain connectedness properties. And it was a really awesome summer spent in sort of puzzling out those questions and writing a couple of papers over the next year on the topic. I ended up moving on from graph theory to topology, or sort of more set theoretic side of the topological realm, and ended up doing more on the foundational side of topology. So did quite a bit of set theory and logic. And as I joined Eliiza and started working with text, it was really awesome to see how both sides of my research, the graph theory side and logic and set theory side, were coming in specifically into problems relating to text and text processing and natural language understanding and various natural language processing algorithms seemed to sort of rely heavily on both logic and graph theoretic structures of it. So what I wanted to do today is sort of walk you through on some of the projects that I worked on where graph theory has come in, and also something that I find interesting in general and would like to work on in the future. To give you sort of a broad idea of some of the use cases that have come in my work, but also hopefully give you sort of a more general overview of some of the use cases, and perhaps what the role of graph theory in these use cases is. So what are graphs? Well, what they're for, to start with that, is they're really, really good at studying relationships between entities and objects. So if we're able to visualize our entities or our objects that we're working with in this structure where relationships between them are nicely apparent, then it makes working with them easier and visually intuitive. And like for me at least, visually intuitive things are just generally making things making more sense and like helping sort of get to interesting insights. So graph, formally speaking, is a pair of sets. A set of vertices, or they could be called nodes. I will probably be using nodes and vertices interchangeably and won't notice it. So V is the set of nodes. In other words, the objects or the entities that we work with. And E is the set of edges or relations that shows how these entities are connected. And graphs can be of different types. Most common, simplest way of seeing them are the undirected version of them. So the connections or the relations between the objects don't have a direction. For example, in the top graph, we have the vertices A, B, and C, and they're just pairwise connected. So when we write E as the as collection of three pairs, the order doesn't matter. We could write, instead of pair A, B, we could write BA. So that would denote the same relation. So what would be a good example of an undirected graph in real life? For example, a social network. If you're friends with friends with someone on Facebook, then they are friends with you as well. So it's a relation that does not go in one direction, it goes in both directions. On the other hand, we could have a graph where the direction of the relation matters. So those would be directed graphs. So on the second picture, we have graph with the same set of vertices, but in this case, the edges between them or the relations between them have a direction. And in this case, when we write down the set of edges, the order of the letters in the pairs matters. So you can see that C and B are connected bidirectionally. And in that case, we include both BC and CB pairs into our directed graph edge set. What would be an example of a directed relation? Say familial relations. So if George is my brother, then I'm not his brother. Or if Nina is my mom, then I'm not Nina's mom. There would be a different relation that would be connecting, that would be initiating on my side and ending at my mother's side. You can also have multiple edges between nodes. And we could have edges that have different weights. And things like properties like this of graphs comes in handy when we discuss networks such as road networks, for example. You could have multiple different paths connecting two cities. And some of the paths can be longer, some of them can be shorter. So that would correspond with weights of nodes, sorry, weights of edges. And you could have weights of nodes to be the size of the city or whatever might be appropriate. So any questions up until here? All right. Always feel free to interrupt me if you have any questions. I'm always happy to answer stuff on the spot. In the context of data science, I think we can roughly divide types of data into the types that have graph structure as their primary structure. So if they come in as a graph to begin with, and the types of data that don't really apparently carry the graph structure yet, but we could, in theory, sort of mine that structure out of data and sort of order or organize the data into a graph. So I will mostly be focusing on the second type because I find it very interesting to discover graph structure and sort of this process of ordering the information in the data into a graph structure I find very interesting. But the realm of graph structure data is huge and very important and very interesting, and it contains things like modeling pandemic spread, or studying social networks, or working with energy grids or various infrastructural grids to sort of optimize supply chains, sort of a plan for efficient infrastructure construction, and so on. So various optimization algorithms come in very handy, and there could be many separate talks on this topic, but for this talk, I will not be focusing on these types of data. When it comes to tools available for using, when it comes to tools available to use directly with data that's structured as a graph, we have several options. If you have sort of a smaller graph and you can just run some of the graph algorithms on your local machine, then Python's NetworkX is an excellent choice. It contains really excellent coverage of graph algorithms. But if your data is quite large and you would like something highly optimized for speed and efficiency, then you could use some of the graph databases such as Neo4j or Kraken, and they have a whole lot of built-in algorithms for you to use, and they're sort of optimized for you to query a graph in a very graph-friendly way. And for example, if you're working with network data or any sort of network data that we listed in the previous slide, it would be appropriate for you to use a graph database and interact with the data through a graph database. I classed the text data in the same among the same type of data where we have graph structure available, but this is sort of a gray area because it depends what structure we are talking about. If we are discussing, maybe I can, no, can't make this bigger. I can. Can you see it bigger? Is it bigger for you?
Yes.
Yeah, awesome. Yeah, so if we're talking about a sentence structure, something that we all learn as part of a grammar class, I think we have all come across sort of decomposition of a sentence into its part of speech, into its dependency diagram that also shows some of its part of speech tags. And in that sense, text can be sort of with minimal processing converted into a graph structure. In this case, the structure is a tree. Tree is a special kind of a graph. A undirected acyclic graph would be a tree. I'm sure people with computer science backgrounds or having worked in data science have worked with directed and acyclic graphs that sort of are really good at describing flows of information or flows of nodes into a pipeline. So if you take out that directedness from the equation, you just get graphs. On the other hand, you could sorry, you could get further into the examples of text where we can view text as requiring quite a bit of processing to get to its like different kind of graph structure. So what I wanted to spend a chunk of this talk's time is to sort of give you a use case for processing text to get a knowledge graph. This is my favorite thing in the world. So you can see sort of a bit of text that's describing the Radch Empire and its leader, Ana Mamatelashvili. And on the bottom, you can see sort of a structured way of conveying the same information. But in this case, we have identified the objects mentioned in this piece of text. We have identified the attributes of those texts. For example, the Radch Empire is a geopolitical entity, or thousands of years ago is sort of a date, not exactly a date, but it's sort of in the same broad type. And Ana Mamatelashvili is a person, and so on. And we have identified how these objects are related, or at least the relations that the text conveys. But what I find really interesting is how do we go from the text that we have into this structured graph that conveys the same information, or sort of close to, or essential parts of the information that text tries to convey. So what I wanted to do next is just like walk you through some of the steps of how to go from the text to the graph, and then how can we query, or how can we answer questions using the graph rather than searching for the answers in the text. One of the really interesting and broad popular applications of this would be knowledge graphs backing chatbots, or any sort of question answering application would benefit from having knowledge structured into a more accessible form, such as a graph. So a workflow for constructing a knowledge graph is rather intuitive. You need to figure out two things. You need your edges or nodes, and you need your relations, or sorry, I said vertices or nodes on the one hand, and the connections between them, or relations, in other words, edges. So in order to get our nodes, which, as we said, would be all the objects mentioned in the text, we want to detect the entities. And entity is just another word for sort of like special objects in your text. And it's also a term used in natural language processing. And there are a lot of different natural language models available that would come in handy to accomplish all of the yellow tasks in this workflow. So we have all of these language models available because sort of the text is given in English. English language is something that we all use. There's a whole lot of language data available out there. It makes sense for you to build one or several versions of sort of basic English language models, and then reuse them for all text related data, with maybe a little bit of sort of last layer tweaking to adjust to your specific domain. But as sort of a core English model, it's good practice to reuse pre-trained existing models, which is what I'm doing for all of these steps. One of the models I'm using is Spacy's large English model. Spacy is sort of broad language processing library that offers pre-trained models for English and really good models in English, but it's also really focused on providing language models in other languages. Those models offer like several really interesting functionalities. And one of them is the entity recognition. And if we run this text through Spacy's entity recognizer, what we get is several noun phrases that have been identified as different kinds of entities. So we have the Radch Empire as a geopolitical entity, a date, a person, and a cardinal, just a type of a numeric entity. You could have, this indicates like the number of something. So at least two, so it could be 2, 3, or more. It could also have ordinal types of numerics, which would be first or second or third. So those would be ordinals. Okay, so that was pretty straightforward to just run text through entity recognizer and get all the entities you want. Of course, if you're looking for some custom entities, you might have to do some extra training on top of that to build your vertex set. But in this case, it was just like using a generic English model, which gave us our vertex set. So we're down for half the graph, sort of. We have all of our nodes or vertices. Now we need to get all the edges. And edges in the case of a knowledge graph come from understanding how these objects are related. So in terms of English grammar, that's just trying to figure out what are subjects and objects for each of the verbs, roughly speaking, or verb phrases, roughly speaking. And another sort of really general large English language model offered by Stanford's CoreNLP gives such functionality. So it's open information extraction part of the CoreNLP model. So again, we take this text and run it through this model, and it gives us several relation triples. So these triples come with subject, relation, and object bits. And you can see there are several versions for parsing sentences. So you can notice that Radch Empire was created thousands of years. It's sort of like not quite the best way of parsing it, but the second option for the Radch Empire is probably the best. So maybe that's the one that we will pick to include among our relations. And then we have similar the relations identified for the leader and under me and I. And lastly, what we should do is try to link together anything that we might have doubled up on. For example, you can see the penultimate relation. She is divided in at least 2 factions. Mentions, so has a pronoun in it, and is referring to Ana under me and I. So she wasn't one of our objects, and it's in itself, it's not an object. It's sort of something that denominates another object. So what we want to do is we want to identify what all of these anaphoric expressions or expressions that refer to something else are referring to. So another CoreNLP, oh, sorry, this is not OpenAI. I should have deleted that. It's just CoreNLP's coreference resolution bit. So CoreNLP offers detection of coreference clusters. And again, we run the text through these clusters, and it gives us 2 clusters. The Radch Empire, which is later, which in the second sentence is referred to with this pronoun, and Ana under me and I, which is referred to the leader and another pronoun here. Okay, so having resolved these coreferences, we can now build our graph. Of course, in reality, you could have you would have a far more complicated graph. You might have multiple different types of relations. So in this graph, we just have types of objects. So in this case, like geopolitical entity and a date and a person, there are different types of objects. You could have types associated with relations as well. You can have attributes for all of the for your objects. For example, in addition, a type would be an attribute. So for example, the Radch Empire has an attribute that it's of type geopolitical entity, but it could also have a different attribute, say how large it is, how many galaxies it includes, or things like that. So you could try to sort of cram in more of the structure, more of the structure of the knowledge in your text. Another side to knowledge graph structure is figuring out a way to query the information from the knowledge graph. So suppose we sort of structured our text, and then we were asked the question, when was the Radch Empire founded? Can we use some of our natural language processing methods to answer this question from using the graph? So first thing I would do to query database is try to turn this question into a query. So we would like to figure out what object we might be querying our database for, and an action that we're querying for. So to look for the objects, you could run the question through Spacy's noun phrases detection, and it will return the Radch Empire as the only noun phrase in the question. Then we could try to, in order to figure out what is it that we're asking about the Radch Empire, we could run this question through Spacy's parts of speech tagging, which will tag each of the words with what kind of, with parts of speech, obviously. And that would mean it will give us if it's a verb or a determiner or a noun or a verb. Well, I already said verb or adverb, and so on. So you can see that in this particular case, it found only one verb founded. And what we want to do next is sort of make sure that this verb is connected with the noun phrase that we detected earlier. And that can come from, again, Spacy's dependency tree. We already saw a dependency tree a few slides ago. And here is another dependency tree for this question. And we can see that the verb founded has the Radch Empire. So you can notice this bit here. Nope. I can't really. So this bit, the Radch Empire, is the noun phrase that's directly dependent on the verb founded through this arrow here. So we can see that the Radch Empire is what this verb is referring to. So now we have sort of parsed the question, and we know we're trying to understand the object Radch Empire and the relation founded. So what we would do is we would go back to our graph. I probably should have included the graph here, but that's okay. I have it here. So what we would do is we would look through our graph, find the Radch Empire object, and then look at all the relations that are associated with it. In this case, was created and is the leader of, and see if we can sort of find a good match for the verb founded that we got from the sentence with any of these relations. So what we can do with this is try to detect semantic similarity or similarity of meaning between the verb from the sentence, founded, and the relations that we have in our graph that are associated with the object, the Radch Empire. So we ran a bunch of these relations through, again, Spacy's word embeddings feature, which comes from the global vectors model that Spacy uses. And we get vector embeddings for each of these verbs, and then we can calculate similarity between those verbs to see which are the best matches in terms of meaning. And we can see founded and created are the best pair with the highest similarity score. So by having found the object, identified the relation that's closest to the relation mentioned in the graph, we arrive at the answer thousands of years ago. Any questions for this part? No? All right. Okay, so this sort of describes one use case for how you could take data, in this case, text, and sort of extract not very obvious graph structure from it, and then hopefully it will make some of your problems easier to solve. So for example, if we wanted to build a question answering application or a chatbot for the Imperial Radch universe, we could parse the ancillary trilogy books and sort of structure all the knowledge in it, and then hopefully back a chatbot with this with such knowledge graph. So far, I have focused quite a bit on what graphs are and how we can build them and how data can be seen as graphs. Next, I would like to sort of give you a quick overview and maybe hopefully give you a little bit of an idea of why that's good, why that's useful, and why would we want to have data in graph structure in the first place, and where does the graph theory come in and make things easier. So I'm going to sort of jump back in time for a bit to 1736, when Leonhard Euler answered a long-standing question about bridges of Königsberg. So Königsberg is a city, I believe now it's in Russia, but it used to be in Prussia before. I will have to double check that, not sure. And it has a river going through it, and the river divided the city into 4 parts of land, and there were 7 bridges connecting these parts of land, 4 parts of land. And the question was, can you pass through all 7 bridges exactly once in your walk? And well, Euler answered that question in negative by realizing, first of all, that it doesn't matter how large the pieces of land are. You just need to associate a point or a vertex with them. And then the bridges would be connecting those vertices. So we can turn the picture of Königsberg into a graph like so. And then the question turns into a graph question. Can you pass through all the edges exactly once? And this is sort of how graph theory came to exist. It's probably the first graph theory question. If you think about it, you can quickly realize that in order for you to keep going with your walk, you would you take a bridge into a piece of land, and then to get out of the piece of land, you have to reuse that bridge again. And every time you visit and a vertex, every time you visit and leave a vertex, you have to like use up 2 of the bridges. And if you want to have your walk be comprised by visiting and leaving a series of vertices, what you could have is a potentially odd number of vertices at your starting piece of land and potentially odd number of vertices at your ending piece of land. But all the middle vertices in your path that you visited would have to have even number, because you would have to visit and leave each of the vertices in the middle. And you can only have the odd number of vertices at the start and the end points if those 2 are not the same. If you finished your walk where you started, then all of the vertices that you visited would have to have even number of edges. So if it was ever possible in a graph to cover all of the vertices in a single walk exactly once, then you would have to have either 0 or exactly 2. Sorry, did I say vertices earlier? If you want to cover all the edges in your walk, you have to have either 0 or exactly 2 vertices vertices having odd number of edges coming out from them. And you can see that in this graph, we have 4 vertices with odd number of edges. So answer to the question is no, we cannot go on a walk and cover and visit all of the bridges exactly once. So what is, this question does a really good job of demonstrating what graph theory is all about and why it is so helpful in optimizing your algorithms and why it is so helpful in computer science. It takes this question of can we do a walk with a certain property? And that question sounds quite difficult because then you have to consider all of the possible walks, and there's a huge number of possible walks you could take. And it would be, in order to brute force the answer to this question, if you're trying to write a code that would brute force answer to this question by checking every single possible path, it would be very computationally expensive because you would have to iterate over a large number of possible paths. But on the other hand, Euler gave us this theorem. He didn't just answer this single question about this single graph corresponding to a single city's bridges. It gave us a theorem saying exactly when is it possible for you to be able to travel through your graph and visit all the edges exactly once. He gave the answer to that in terms of just counting the number of edges coming out from each vertex. So now we just have 4 vertices, and we just have to check the number of edges for all the four vertices. So in any graph you consider, just counting, just checking a property for the set of edges versus checking the property for all the possible paths is of very different order of magnitude in terms of complexity. So to me, the way I see graph theory is it provides these bridges between problems where we have to check something in a huge set versus problems where problems that are reduced to checking something in a small set. So these kinds of characterization theorems where we have sort of correspondence between iterating over a large set being the same as giving the same answer effectively as iterating over a small set, is why graph theory is interesting and why it is so helpful. So as when I started this talk, I mentioned a puzzle that I worked on in like beginning of my maths research journey. I just wanted to tell you what the puzzle was, because it does exactly the same thing as I described. So it's like a very, very core graph theory sort of question. I'm quite proud of having figured it out, because it does a very similar thing of taking a problem where you have to check something infinitely many times versus check something 7 times. So what I was working on was a bunch of finite graphs, and we were studying sort of these strong connectedness properties, where we define a graph to be n are connected if for any n points you put on the graph, there is a path that goes through all the points, and the path is restricted to sort of non-self-intersecting paths. So you're not allowed to go through vertices twice, while in the case of Euler's question, you were allowed to pass through the same vertex twice, just not the edges. After solving a series of puzzles, we arrived at an answer that actually, if you're looking for really well-behaved graphs where graphs are n are connected for all natural numbers n, then all you have to do is check if it's one of those 7 graphs. Yeah, just wanted to tell you about this. And there's a link to the paper if you want to see more on that. So what I would like to do next is sort of give you a quick overview of some of the graph algorithms that came in handy. Graph algorithms of similar nature, of like being able to relate sort of 2 sets of different orders of magnitude as your things to iterate over. And just give you a few more use cases on these specific graph theoretic algorithms. So next use case comes from another project that we worked on, where we had an information extraction problem. We had a bunch of pharmacy receipts, and we wanted to sort of process that receipt and get information such as the drug that was prescribed, the address of the pharmacy that was prescribing the drug, the name of the patient, the amount paid, and so on. So what we used for addressing the problem, for part of addressing the problem, was the connected component search algorithm for graphs. So what that algorithm does is it goes through, considers the node sets and returns the sets of nodes that don't have connections between them. So in this case, in the graph given below, you can see nodes 1, 2, 3, 4 are connected together, but they're not connected to another component made out of 5 and 6. So in this case, we would have 2 connected components. So what we did for the information extraction problem, we represented the text on the page as a graph by declaring words to be nodes. And we defined like a specific proximity check between 2 words to decide whether or not they were close enough to be declared as connected, and then ended up getting a bunch of sort of connected pieces of sort of densely connected pieces of text. And I'm really glad Patrick is here right now, because we had quite a few chats about this, and he had really awesome ideas on this topic. So it was his suggestion to like try out a few of the proximity measures. So that was really awesome. Thanks, Patrick. I will I've mentioned this a few times as well. So it's like really nice to have Patrick to work with on this. And this specific sort of dense text identification of the page is helpful if we want to detect things like blocks of text, such as address, or in this case, I think there are 2 addresses identified. So that gives you sort of this blob of text, and then you can sort of go through a bunch of blobs of text and check which of those blobs corresponds to an address. But you can be sort of, if you are reasonably certain that your pages have a specific layout where the address is often written as like a dense piece of text, then this connected component algorithm will sort of help you get those chunked out together rather than going through the text line by line. Another project where graph theory came in handy was trying to summarize articles or links of articles posted in our Slack channel. And this is another project that I worked on with Patrick. I'm so glad Patrick's here. So what we did for this project was, again, we took the text of the article and represented as a graph by declaring sentences to be nodes and semantic similarity to measure whether or not there was an edge between them, or rather, what was the weight of the edge between them. So if the 2 sentences were discussing a similar topic, so if they were semantically similar, we would have an edge between them that was of high weight. And then we ran a PageRank algorithm on it. What PageRank algorithm does is it tries to identify central nodes in your graph. So nodes that are connected to lots of other nodes, but it also considers the weights of the nodes. So something that if you were traversing through your graph and following the paths with high weights, you were highly likely to arrive at those nodes. So by running a PageRank on such graph made out of sentences from the article, we ended up getting sort of top few sentences to represent the summary. So represent a top few central sentences that sort of conveyed most of the meaning in the article. I'm quite conscious of time and I'm almost done. Just one more slide where I just wanted to mention just a few more algorithms, such as graph coloring algorithm that comes in handy if you want to divide up your graph into sort of pairwise disjoint groups with certain constraints. A click identification algorithm. A click is part of a graph that has an edge between all pairs of a subgraph that has edges between all pairs of vertices. So in itself, it is a complete graph. And clicks are really good at detecting sort of clusters in a social network. Next few algorithms, such as shortest paths, minimum spanning trees, and planar graphs are really interesting if you're doing infrastructure network planning, and cut sets and connectivity are also coming in, various network flow questions, and also coming in handy if you're doing infrastructure planning sort of projects. So I think that's all I wanted to cover today. Thank you very much, and I will leave some time for questions. Or back to Marcus.
Thank you, Nuchki. So while you were talking, we have had some questions in the chat. And Patrick asked, can you have more than one edge between 2 nodes?
Yes, so that would be a multigraph. You can absolutely have that.
And what does a multigraph do? It doesn't make any intrinsic sense to me to have more than one connection between 2 nodes.
So if you consider, say, network of cities with roads between them, or like say airline or airport networks. There will be multiple flights connecting to airports. So if you're trying to, yeah, if you're trying to like plan for traffic or measure traffic flow, that would make a difference.
And then also Patrick, who's been very prolific, how do you sample a network?
Would you elaborate on that, Patrick?
Yeah, sure. So, like in the real world, often if we want to like look at someone's social media, if we want to make like a social network, we don't. I think part of that process involves like constructing a graph, but the entire graph of a social network wouldn't fit inside our laptops. Because there's 7 billion people. So like, I guess I'm wondering, like, are there any techniques to kind of look at some sort of network structure in the real world and infer and get like a sample of the graph, the same way that we can sample other kinds of data?
Yeah, really good point. To be honest, I have not considered that at all. So I would be really speculating if I tried to answer that. Of course, just purely from graph theoretic point of view, you could look at a subgraph. So whatever vertices are inherited within the subgraph, that could be a way of sampling. But again, I don't know what are the pros and cons in practice of such an approach of like sampling random set of vertices and then just taking all the inherited edges between them. But yeah, don't really have a good answer to that. I would have to look into it.
It's probably also quite interesting to consider that you could resample a graph in order to make connections more easy. For example, if A is connected to B, to C, to D, and A and D are multinodes which connect to a lot of other points, that you skip all the ones in between. But questions. So, Subodh, sorry if I pronounced this wrongly, did anyone apply graph theory in author profiling doing NLP?
Is that a question to everyone?
Yeah, sort of.
Yeah, I haven't done that.
And then we have Patrick again. Can you create a knowledge graph of a GitHub repo?
Yeah, that's really interesting. Are you asking if I can? Or can you in general?
Yeah, like, I don't know, would it be a good idea to, could some graph theory expert create, like, is, source code amenable to this graph theory approach? And
yeah, so what I found trying to attempt to create a knowledge graph from scikit-learn's documentation files, it's a very labor-intensive job, and I suppose there will be like trade-offs to make there. If it's a huge, what kind of huge repo would you have for it to make it worth your time to invest, like cleaning and structuring it into a graph? I think it like really depends on your specific question, but yeah, you absolutely can.
Yeah, right. And knowledge graphs generally hand curated?
They don't have to be. I think it's good to like start them off with pretty, think from what best practices sound like. Good first start would be to have sort of pretty clear, predetermined structure of what node types should be, what are the relation types, even have sort of restricted number of relations. So when we were looking at the text example, in theory, you could have any verb could serve as a relation, but it probably is a good idea to not allow this, but rather have sort of types of verbs that you're only just have like specific types of relations you're allowed to have. And then if you can start with a graph like that, then from then on, you could sort of have a bunch of more probabilistic approaches to discovering new entities and new relation types. And that would involve sort of cross-checking your knowledge from different parts of the different sources of knowledge. So, for example, if you're like parsing internet text, internet could contain wrong information. So you don't want to just automatically parse that and add that to your graph. You want to be able to like double check that it's correct. So have like several, some degree of confidence in your graph. So I think a bunch of graph building techniques. There are a bunch of automated graph building techniques that rely on scoring your confidence in the new facts, and it's also could rely on things like recommender systems that suggest that, oh, if these two vertices are sort of similar, they ought to have a relation like so between them. So yeah, I think there is quite a bit of an interplay of methods where you can like automate building your graph.
And now we're hitting a few questions with regard to the empire of Radch. And Alexander would like to know, if the text is a story, can a sequence of graphs be a kind of time series which represents the story?
Okay, I would look into modal logic for this, to be honest, because that sort of offers this sort of time element to your structures. I would not go into too much details right now because I honestly don't remember. Can't really think of like what would be a good way to using that. But like first thing that comes to mind is modal logic, and ideas from there could be helpful.
Lovely. And next up, we have Noon, who would like to know, if you have to compute a lot of edges for that sentence similarity one, did you actually compute all of them?
I think I did compute all of them for that one, but I really should have only computed the ones that were attached to the Radch Empire.
Lovely.
I actually mean you were talking about a Slack bot.
Oh, yes, all of them.
When you?
Yes. In that case, we would compute similarity between all pairs of sentences. Yep. It was not too bad.
Sorry, Noon, I misrepresented that one. And next up, we have John, who would like to know if there's an advantage of the knowledge graph approach compared to the traditional logic programming system, like, for example, Prolog.
Yeah. So doesn't Prolog have to, so don't you have to sort of load information into Prolog to begin with? If you don't mind sort of elaborating on that, John.
Yeah, so it seems to me, so first, thank you for the very nice talk. Can you hear me okay?
Yeah.
Yeah, great. So it seems similar to, I mean, so the answer is yes, you have to declare the things that are true in your world, so to speak. But of course, you need to do that for the knowledge graph as well, don't you?
Right. Yes, of course you do. Yeah, good point. I would have to consult computational aspects of things. I think knowledge graphs like Bracken and Neo4j are optimized to be quite fast when you're querying things. From my use of Prolog's quite slow. But of course, I'm sure we can think of cases where Prolog would be better suited.
Yeah, right. So,
yeah.
So just, I guess it's, I suppose Prolog uses a kind of built-in breadth-first kind of search or something like that. But I suppose if you had the graph yourself, you could search it in whatever way you wanted. And so in general, you have more of a kind of fine-tuned control of the structure. But I guess in that sense, it's less user-friendly for the average kind of pedestrian programmer and person who wants to query the database. Yeah. Right.
Yeah. I mean, it's a tool. It's appropriate for some cases, not appropriate for others.
And the second part of his question was that you mentioned that you use the semantic distance between two words. Is there an easy way to explain how this is defined?
Yes, absolutely. So what word embeddings or word vectors are trying to achieve is they're trying to look at all of the words that we have, and in context, in texts where they appear together, and try to identify sort of latent dimensions that decide closeness and meaning. So, for example, Patrick and Nushki might be quite close in the semantic similarity sense because we have worked at the same company. We are both data scientists. We are both humans. We both have like we have 2 legs and 2 hands. So if we don't know what exactly the glove model or any sort of word embedding model decides what those latent features are, but they could be things like, is this object a human, or is this object I don't know, something else, or is this object green, or things like that. So it takes all the words and sort of maps them into a smaller number of features. And then if we have those features in common, if the objects have those features in common, they'll be semantically similar. So they'll be closer in meaning.
Okay, so just to follow that up, so is it, I mean, I don't use any of these tools. But so in the natural language processing, ecosystem, there are tools that will, there are kind of databases of these kind of latent features for a large number of English words. Is that right?
Yeah,
and then you can,
that's right.
Right. Okay. That seems very, like, I guess how else are you going to do it, right? But of course, if you have a word that isn't in that database, then you won't be able to do anything with you won't be able to say how semantically related 2 words are. So it seems, yeah, I mean, how else are you going to do it, right? So I don't know.
Yeah, so you could if you have access to a bunch of text that contain that new word, you could retrain the model, and then you would include that word.
Oh, I see. Okay, so it's not. Yeah. Okay, I see. So yep. Sorry.
Yeah. So there are ready-made models, which I use the ready-made one, but you could train your own.
Right. So I guess what wasn't clear earlier that I think is now is that these relations, these latent kind of relationships, are all, you just put text into some machine learning model, and it figures out what those relationships are.
Exactly. Yeah, and it figures them out based on whether or not they appear in the same context often.
Oh, okay. That's interesting. Okay, thanks. Yep.
Yeah, no worries.